Welcome to this episode of Eureka, and we are going to have a very exciting and a very informative conversation with Dr. Dibyendu Nandi, who is the head of the Center for Excellence in Space Sciences, which is part of the IISER-Kolkata. Space weather is one of the hot topics today, and they have established a world-class center in this place. Before we start our conversation, let's take a quick look at his brief profile. Keep watching Eureka.
Understanding our space environment and how the sun's activity influences space weather and planetary atmospheres is vitally important for the protection of our space-based satellite assets and space-reliant sectors such as telecommunications, civil aviation and climatology. Dr. Dibyendu Nandi is leading India's efforts in the development of indigenous space weather forecasting capabilities through novel computational modeling and data analysis techniques geared towards understanding the Sun-Earth system. Currently, Dr. Dibyendu Nandi heads the MHRD-established Multi-Institutional Center of Excellence in Space Sciences India at IISER-Kolkata, and is chair of the International Astronomical Union Working Group on impact of magnetic activity on solar and stellar environments. He received his BSc degree from St. Xavier's College, Calcutta University in 1995 and received his PhD degree and Martin Forster Gold Medal in 2003 from the Indian Institute of Science, Bangalore. Dr. Nandi has made seminal contributions to the study of the origin of the sunspot cycle and in understanding the sun's coronal structure and dynamics of solar magnetic storms, which critically influence our space weather. He is currently developing India's national capabilities in computational modeling of the interactions of solar and stellar plasma winds with planetary atmospheres, which have important consequences for planetary climates and habitability. Dr. Dibyendu Nandi has published many articles in renowned journals, and his honours include the Ramanujan Fellowship of the Department of Science and Technology, Government of India, and a Parker Lecturership, and the Harvey Prize from the American Astronomical Society.
Thank you for being with us. It's a very interesting place. I mean, lots of young people, and you're working on one of the hot topics actually about sun, right? I mean, hot sun and its effect on not just on Earth, but also the in-between space. I can understand that why we should worry about weather. I mean, if there is going to be a huge cyclone, I mean, we may need to evacuate people on that coast. If rain is going to be less this year, we need to plan our food grain, store it so that, I mean, maybe we may not have good harvest, and then we need to feed people. But except for curiosity, do you think we have, how does space weather impact us on our daily life today?
Thank you for having me on the show. India is fast developing into a nation which is critically dependent on space technology. And you brought in this issue about global weather, which does, like cyclones and weather, rainfall, it does impact our agriculture. We are also now actually utilizing satellite imagery and space-based technology to understand crop patterns, the yield of crops, as well as trying to make the fishing more efficient, right? This is just one example. If we just also look at how the modern society has developed, you know that we use cell phones, which also critically depend on something known as telecommunication, which relies on satellites up in space. And you have heard about the INSAT satellites, which is something that India is very proud of. So we are self-reliant in this. But what it also means is that as we have more and more assets in space, we should also start worrying about protecting those assets in space. And the space is not a vast empty void as we often have and get to hear. I mean, so if you are near an active star like the sun, the sun's output actually varies in time, and its radiation, energetic particles and magnetic fields from the sun actually creates a changing environment in space, which is known as space
this
weather.
Brings me to this question. We use this phraseology, space weather. When we talk about weather on surface of Earth, we talk about rain, maybe we talk about sunshine, maybe we talk about temperature, maybe we talk about some weather phenomena like thunder or lightning or even hurricane. Okay, so when you talk about space weather, there is no air, right? There is obviously no clouds. So what is it that we mean by weather? I mean, what are we talking there?
Right. So just like the Earth's atmosphere, you normally have atmosphere with oxygen, nitrogen, carbon dioxide, winds in the background, which is not very, let's say, not very intense winds. That's sort of the background weather that you do not worry about, you take it for granted. Yeah. Just the same way, in space, there is something known as the solar wind.
Okay.
So the outer atmosphere of the sun from the hot corona, the plasma material that exists, ions and electrons, they are slowly expanding and moving out of the sun in the form of a solar wind.
Okay.
And so this solar wind forms the background environment of the Earth and any planet which sits in space, which we normally do not worry about. But in this background space environment, which is filled with this energetic ions and electrons which are flowing at about 500 kilometers per second from the sun through the interplanetary medium, there are also sudden transient events called space storms.
Okay. So
the space storms are like the hurricanes or a massive cyclone or a tornado, which creates hazardous space weather. And these are the ones that we mostly worry about because they bring enhanced radiation, high energy radiation in X-rays and extreme ultraviolet. They are also accompanied by a large flux of energetic particles in space, which can impact satellite operations and screw up their electronics. And this is a problem that we need to worry about. And therefore, there's this thrust to understand the weather in space and be able to predict this so that you can predict the space assets.
So what you mean to say is that the prime driver of space weather around Earth is sun. So which means that you need to understand how sun functions.
Right.
Whether the sun is, with a small variation, it is just emitting energy, or there is some sudden, eruption of high energy particle from some part of sun. Right?
Right.
Suppose if it is coming from the other side of Earth, we don't worry because it may not necessarily hit us. Am I correct?
Yeah. Well, so there is nothing like the sun on the other side of the Earth. So the Earth is in orbit, and so we know that the sun is in the center, and the sun is the most dynamically important astrophysical object near us, which has an activity whose influence expands beyond the physical dimension of the object itself.
Yeah.
Right. So and this is the same story in every system where you have stars and planets. The star is the most active, right? So we have to worry about the sun because the sun is what is creating this weather in space, as you correctly identified. So this means then we have to, both through observations as well as theoretical modeling, try to figure out why does the sun produce this activity which manifests as space weather, and beyond this normal background solar wind, when and how are sudden solar storms or magnetic storms from the sun created? And can we understand this well enough to be able to finally do predictions, which is the holy grail of this sort of kind of sciences.
So if you can predict, then it means that you can protect your system. Maybe exactly. You can switch off your satellite so that the electronics are not,
yes. So
or you can make whatever you need to make on surface of Earth. I mean, maybe you know that you are going to have a blackout at some period, so you
right.
take care of it.
Yes.
Yeah. How do you actually model the sun and then predict it?
Right. Okay. So to model the sun, we have to understand the physics of the sun. So what we know is that the energy is generated in the core of the sun through nuclear fusion, and this energy propagates out from the sun, and finally when it reaches the surface, it's radiated away. Now, the temperature inside the sun is so extreme that matter is ionized. So normally our atmosphere is neutral. So atoms are neutral because they have electrons and ions which are in balance, right? So when you energize such atoms at very high temperatures, they break up into electrons and ions. And when you have a large number of electrons and ions, then you have a system which is known as a plasma system. Yeah. So the sun is made of plasma. Okay, and when you have motions in such a plasma system, then you constitute large-scale currents. And when you have these large-scale currents, then you can produce magnetic fields, which basically follow from the famous equations of Maxwell. Yeah. Right. So essentially, you have to build a theory based on the system of plasma flows, and the system is known as magnetohydrodynamics. Okay. And we rely on equations developed from the Maxwell's equations for understanding a magnetodynamic system, and then we code that into a computer, and we assume certain geometry appropriate for the sun. We take properties of the sun's interior and we fit that into a computer, and then we solve these equations to understand how the sun is producing the magnetic fields. Okay, so that's one part of the story, and the second part of the story is once you've created the magnetic fields, how do they erupt and form storms?
Yeah, that's a place where we will take a very short break. Don't go away, keep watching Eureka. After this break, we are going to discuss with him how this team made a prediction in a recent solar eclipse, and then it was close to the reality that was observed. So which means their model is closer to predicting level. We'll keep discussing this after this break. Keep watching Eureka.
Ghata, one of the oldest and most unique percussion instruments of southern India. You can play it not only with your fingers, but palms, wrists and heels as well. You'll be surprised, but the air inside the ghatam reverberates, creating the musical notes. 5 elements of nature, earth, water, air, fire and space, make up the composition of this beautiful musical piece, which has found an apt place in most of the ancient books.
Welcome back to Eureka. We are having a very wonderful conversation with Dr. Dibyendu Nandi, who is the head of Center for Excellence in Space Sciences, which is part of IISER-Kolkata. Before the break, we were talking about your recent work, the so-called Great American Total Solar Eclipse, where you predicted what would be the shape of corona even before the actual eclipse took place, and people were waiting to see if your predictions proved right. So I have 2 questions. One, why did you want to predict the shape of corona, and how do you think that is going to indicate us the space weather?
Right. Okay. So there are 2 aspects to this prediction. So one aspect is to actually build models which will help you make predictions for solar storms which are created in the corona. The other aspect was more fundamental. It was to actually test whether the theories and the models that we're developing for the sun's activity actually match up to observations or not. Okay. Right? So we proceeded with these 2 different ideas in the back of our mind. And eclipse is sort of a beautiful phenomena which allows you to see the sun's outer atmosphere, which is very faint otherwise, and you don't see it during normal times, right?
It's there, but we can't see it.
You can't see it. So once you see the structure of the outer atmosphere, which is the corona, through observations during an eclipse, you can match the structure that you see to that predicted by your theoretical models. Okay. Right? So, and we had been developing, this predictive models of sun's activity for a while now, and we were sort of about ready when this eclipse came, right? Okay. And then immediately we decided that this is a beautiful opportunity for us to actually push our modeling to be able to do a prediction and see how well are we doing. So this is what we did, and it doesn't end there. So this is only a first step, right? Which tells us that, okay, so we build a theoretical model that we are now simulating in a computer. If we are able to make a prediction that is now proven by the observation, then we can actually take this model forward and start making predictions for solar storms, the solar wind, and everything else that we're really interested in.
Okay. Now let me come back to this prediction that you made. You made a prediction and then there was a observation. Yeah. You know, the real corona was seen and then people took photograph. How did they match?
Okay, so what we really predicted was the magnetic field structure of the corona, and the corona is a very interesting place because normally you expect that as you go from the interior of a star to to the outer regions, the temperature will fall, right? And that is what happens until the surface.
Yeah.
The center of the sun is 15 million degrees Kelvin, the surface is about 6,000 degrees Kelvin. But then when you go out into the atmosphere, the temperature again increases, right? And it becomes almost like 1,000,000 degrees in the outer atmosphere, right? So, and what happens is this magnetic fields that are actually in the outer atmosphere, it turns out that they heat the plasma and create this 1,000,000 degrees of the corona.
Something like an induction stove.
So it's actually something called magnetic reconnection, where the magnetic field lines reconnect with each other, and the magnetic energy is lost, and that lost energy, we cannot destroy energy. So that energy is transformed into heat and light energy. So you actually, it's kind of beautiful because in the sun, in the outer atmosphere, the layers of the plasma that becomes hot and emit, that you see, are actually attached to the field lines, magnetic field lines. So when you see the corona, you actually almost see the magnetic field lines, which is
well,
amazing.
Like for example, in the school experiment, you put iron filing and then you see, it's very something like that.
Something like that, except that here you're seeing it in emission, where the regions of the magnetic fields are the strongest emitters, right? So essentially, when you're observing the corona, you're actually observing the magnetic fields, which we are now actually modeling in a computer. And that is how you can compare the simulations to coronal observations. And we predicted certain structures, certain petal-like structures in the corona, which are known as streamers. And we largely found that we could predict all the structures, the prominent structures that were observed in the sun. And we also mostly got the location of those structures right. We didn't necessarily get all the fine scale magnetic field inclinations
so
and tilts.
more improvement is required.
Yes, absolutely. I think yes, this was the first.
So which means that if you persist on this line, perhaps someday we will get a good model with which we can predict space storms or weather changes, space weather changes.
That is exactly
much earlier.
That is exactly the idea. Yes.
The other area that your center is interested and you are fast moving in that direction and also collaborating with ISRO is launching a space satellite to observe sun called Aditya, right? So what's your role? What's a specific role of your center in that?
Okay. So the mission is actually called Aditya L1 because this is going to be in a location in space that's called Lagrangian point L1. The L1 point is a unique point close to the Earth, but exactly in between the Sun-Earth line. And so when the Earth is moving around the Sun, this point also is attached within quotes to the Sun-Earth line and moves along with it. So a satellite parked there will always be able to view the Sun, and will always
backside will be always toward
exactly.
there.
So you can do the telemetry to get the data, do the data downlink, right? So. So there was a mission here previously. This was by the European Space Agency called the SOHO mission, and then this is the sort of the a follow-up to this international endeavor to have
permanent mission to observe
from L1.
But if there is already a SOHO, why do we need to send?
So SOHO was launched in 1996 and it's been there for a long time now, and many of the instruments are degrading and is close to being now shut down. So when we do launch the Aditya L1 mission, it will be one of the grandest solar observatories in space, which will not only benefit us, but will benefit the whole world from the observations that.
What is the specific role your center is playing there?
So I am a co-investigator on one of the instruments known as the Solar Ultraviolet Imaging Telescope, which is being developed by IUCA primarily with collaborations from around the country. And I'm also the science lead on the modeling and simulation support for this mission. So when you observe a phenomena, you have to interpret this. And when you interpret the observations, you have to rely on a theory or a model for the system. So we are creating the models that are necessary to understand the Sun-Earth system and how solar storms are created and how they.
So even your involvement in Aditya is linked somewhere to your core area of trying to understand the dynamic of sun through modeling, right?
Exactly.
That's a very interesting point. This whole thing is based on that Earth is having a viable magnetic sphere which can protect us from the harmful rays of solar wind, right? Suppose if there was no magnetic sphere, what would have happened to Earth?
So we would have been gone with the solar wind. So you have the magnetic field of the Earth and any planet that has a magnetic field. This magnetic field traps the charged particles that are coming from the sun, and so they act as almost within quotes like umbrellas, which are protecting the atmosphere. So as long as you have your atmosphere, which is life-sustaining, well within the magnetosphere, then the atmosphere is protected. However, if you either do not have a magnetosphere or you have a very weak magnetosphere and the atmosphere permeates beyond the magnetosphere, then it is subject to erosion.
You mean to say that the solar wind will hit and then it will take away the atmosphere, so slowly your atmosphere will thin down.
That's right. Yeah. So this is called atmospheric mass loss. And so this is the role of the magnetosphere of planets like the Earth. And this is of course due to the fact that we have a liquid outer core, and there are motions in this liquid outer core,
which is largely iron.
Iron, exactly, which sustains this magneto-hydrodynamic dynamo mechanism.
Mars too had a viable magnetic sphere,
dynamo,
right?
Yes.
But then it solidified.
Right.
So would Earth's magnetic sphere also solidify, and then we will lose magnetic field
so
around Earth?
It depends on how long we can sustain the heat energy that is trapped in the Earth. And there is some understanding that maybe some heat is also being created through radioactivity, and I do not believe there is an exact understanding of how long we should be able to sustain this motion, and you have to also understand this motion depends on convection and therefore a temperature gradient as well. That is also important. Not just a liquid core, but also the possibility of motion is extremely important. So both of these have to be sustained.
It's a place where I want to ask you this question. I mean, if you go back and read literature around 1960s, when people talked about planets which are habitable, meaning that planet which can host life, they were looking at for a planet which will be in the right distance from sun. So it is not too hot, but not too cold. So they were essentially looking at the energy falling on it.
That's called the Goldilocks Zone.
Yeah, Goldilocks Zone. That's what usually people used to call it. But then I think that's quite inadequate, right? I mean, that may be necessary, but not sufficient.
So that is only one of the necessary conditions. You also need to have a magnetosphere. This is very important. And the interaction of the winds from the parent star, which carries magnetic fields along with it, which sometimes has this magnetic storms, the interactions of those with the magnetosphere of a planet will define the atmosphere, and will tell you whether it's possible to hold on to the atmosphere and therefore have a sustainable atmosphere for the origin and evolution of life.
So which means that the kind of model that you are building would also be in future useful when we are trying to identify potentially habitable planet, planets going around other stars.
Yes, and this is another sort of new direction that you've taken in the center, because this is something that expertise that does not exist in India. We want to start this this understanding with indigenous models in India. This is to look at the interactions between the parent star and the magnetosphere and atmosphere of planets such as that of the Earth. And we also know that the sun's activity has varied over its lifetime of billions of years. And the young sun was much more active, dynamically active. So what would it have done to the Earth's magnetosphere at that point in time? How does this coupled evolution of a sun and a planet take place? And what are its implications for your ability to hold on to atmosphere? Because this then would have say on whether the planet would be habitable or not. So this is a very important field that is developing very rapidly, and we wanted to ensure that we also develop these models indigenously, which can have provide keys to answers on these profound questions that humanity has to address. Where did we come from? What are the conditions that helped us evolve to these intelligent beings, and is it possible to have life like ours, or even organismal life, microorganismal life in other planets?
Yeah, that will answer the fundamental question of is life just one time in the universe or multiple time? Many questions are linked to that.
Yes.
Let me turn to a different direction here. I mean, Earth's magnetic sphere is what is protecting our atmosphere. Suppose if the convection is not happening, or the core solidifies, I mean, we are going to lose it.
Right.
Is there a kind of estimate like when it can possibly happen? Maybe not tomorrow, of course.
Okay. So if you suddenly stop all the motions or the code solidifies. So you are shutting down the dynamo, which now means that you have a magnetic field at some point in time which is existing, but it's not being sustained anymore.
Yeah.
So what happens is then this process of decay of the magnetic fields take over. And this typical, based on the conductivity of the Earth's core, you can make estimates of how long will this field survive without being created, right? And the typical time scale for this is about 20,000 years. So
20,000 years.
Yes.
Okay, so enough time.
We still have some time to figure out
what to do
and where to go to. So,
okay. So
yes,
what do you think we should do if we come to such a situation and then we are given 20,000 years for Earth to sustain life?
Okay, so I am optimistic about this. The reason I'm optimistic is completely based on empirical facts. The empirical fact is in the last, so when did the space age? 60s, 1960s.
59 is the first
59.
time.
So let's say 40 years, so 60 years.
Yeah.
So see, in 60 years, look at what we have achieved. We did not, we just barely managed to send some small rockets. We have gone to the moon. We have sent human beings to the moon. A satellite that we have built, which NASA built, Voyager, is now out of the solar system.
And we have been keeping humans in the space
for
continuously
years,
for
a year almost, right? I mean, so this has been possible in the span of 60 years, whereas we have reached this sort of this state of intelligent form in something like 3 to 4 billions of years, right? In the existence of the Earth's history, right? We achieved this in 60 years. So I am hopeful that given enough time, we should be able to find
ways of.
Yes, so Star Wars, some of the things that has been discussed or portrayed in Star Wars is not impossible. I think it will be possible to find a habitable planet where you can form the seed of new
See, one of
new
the things that
civilization
people say when this kind of a dream is presented, or this kind of a vision for sustaining exploration of space is presented, is that it's escapism. You don't want to, I mean, you are destroying the Earth. You are spoiling the climate. I mean, there is a climate change happening. I mean, you are killing off life forms. I mean, there is a huge decay of species, okay? And instead of rectifying your mistakes, you are trying to escape and run away. How do you look at this kind of a criticism about this new enthusiasm for space exploration? So
in my opinion, I don't think they're connected. Okay, so I believe that we should not be destroying our planet. This is the first thing. This is independent from trying to find another habitable planet from where we are, right? I don't think that is escapism. I think that is going to become a necessity. If not today, at least in a few billions of years. Now, you may not want to think ahead in that much time scale, but the point is, if generations after generations of human beings do not think about this problem, then when the time comes, we will not be ready for it, right? It is only because somebody had the idea of exploring outer space, sending somebody to the moon 60 years back, that we are here today, and we are managing to utilize and take advantage of the space technology to advance many aspects of our modern society, right? If we had said that somebody is just going to escape to space, what is the need? This would not have been achieved, right? Which is independent from the fact that we should try to do everything that we can that is within our power to help protect this planet from rapid climate change that we are doing as human-made climate change. That's independent. But I think the spirit of exploration is important. Dreaming is important because eventually it will help you, solve a profound question that is at some point in time going to come and haunt us. Is what happens when you lose this about?
Yeah, that's a interesting place where we need to end this interview today. There are lots of things that we can discuss. It's a very exciting and informative conversation. Thank you for being with us.
Thank you very much.
Keep watching Eureka. We'll come back with another interesting conversation next week, same time.